Wow, what a great couple of days this has been. I just love getting to see all the exciting things that all of you are doing with our technology. Over the next half hour, what I'd like to do is reinforce some of the messages that we heard from Jensen Huang in his opening keynote yesterday morning. Now, I've been in the high-performance computing industry for about 20 years, all my career. I spent about 20 years at Cray before coming to join the Nvidia team about 3.5 months ago. I helped design the first machine to sustain a teraflop of performance on a real application code, and later the first machine to sustain a petaflop of performance on a real application code. And now, along with all the rest of the engineers at Nvidia, we're working to create the technology to sustain an exaflop by the end of this decade. Now, an exaflop of computational performance will provide truly transformational capabilities to many important areas of science. There are problems that can only be solved with an exaflop computer that cannot be solved before. Simulating the whole global Earth system at a fine enough level of detail to capture the ocean eddies and the cloud convection and truly understand global climate change and explore mitigation strategies can only be done with an exaflop computer. Understanding from first principles how an engine, a gasoline engine, actually works, large eddy simulation, to truly understand at the fundamental level how it works, requires an exascale computer. This will allow us to build more efficient engine designs and reduce pollution and save energy. Understanding a cell, modeling a cell at every level, from the molecular level to the genetic level to the chemical and biological level, according to the scientists working in this area, will require an exaflop computer. Truly understanding the formation of matter in our universe, understanding supernovae at a fine enough level of detail that we can confirm or deny that the theories about how this process works requires an exaflop computer. So extremely important that we achieve this goal. Now, you might be led to believe that this is fairly easy to do. We've all seen the top 500 list. We've all seen how the performance of the number one machine keeps getting faster and faster every year. The middle line there in red is the number one machine from 1993 to the present day. And if we extrapolate that line, we should be getting to an exaflop computer by 2019. The problem, of course, is that that number one machine over time has been getting larger, it's been getting more expensive, and it's been consuming much more power. The very first number one machine on the top 500 list was the Thinking Machines Connection Machine 5. It used about 200 kilowatts of power. Well, the current number one machine uses about 10 megawatts of power, 50 times increase in power over this time. And of course, much larger, much more expensive. Now, this can't continue. We can't increase the power by another factor of 50 over the next few decades. We think perhaps 20, maybe 30 megawatts is a practical limit for an HPC system. But it's worse, because the underlying technology has taken a turn that's making life much more difficult for us. For multiple generations, for multiple decades rather, we've had what's known as Dennard scaling. Jensen talked about this yesterday morning, where every time we have the size of the transistor, we also have the voltage, and we get an 8x improvement in capability at constant power. It's been beautiful. It's taken us from a megaflop to a gigaflop to a teraflop and almost to a petaflop. And during this several decade period of time, the technology has given us about a 68% a year improvement in performance per watt of the underlying transistors. And we've taken this and we've created processors that have gotten about 50% a year faster. Some of those transistors we actually spent on improving single-thread performance, making more and more complicated processors. Unfortunately, that's done. We can no longer continue to drop the voltage with every generation because of leakage. And now, every time we have the size of the transistor, we only get about a 2x increase in capability. That's only about a 19% a year improvement rate. Very, very difficult going forward. And what that has put us in is a position where we are completely constrained by power. If we put all the transistors we could fit onto a chip and we ran them as fast as we were able to run those transistors, the chip would literally burn up. It would melt. So we are constrained today not by transistor density, not by transistor speed, but by power. And in fact, it's getting worse with every generation. Moore's law is alive and well. We continue to get a quadratic increase in transistor density with every generation of integrated circuit technology, but the energy per operation is no longer decreasing at the same rate. It's only decreasing linearly. So each generation, we're becoming more and more power constrained. And so high-performance computing in the future is all about power efficiency. Now, there are two things we can do to make systems more power efficient. We can reduce the overhead to try to spend more of our power doing the actual work, the adds, the multiplies, the shifts, the compares. And we can try to minimize data motion, because moving data is actually much more expensive than computing. It takes much more energy to move operands across a chip than it does to add them together or multiply them together. So how has the mainstream industry responded to this? They have responded to this by building multi-core CPUs. Let's put multiple cores on one die, and instead of trying to make one processor run as fast as possible, we'll get more of our performance through parallelism. We'll use a slower clock rate. We'll exploit locality on a chip. And this has worked to an extent. But unfortunately, the underlying technology of a CPU was simply not designed for power efficiency. CPUs are brilliantly designed. They are wonderful inventions. But their design, their purpose in life, is to make one thread of computation run as fast as possible. And so as a result, we build very deep pipelines. We have fast clock rates. We build big caches that can deliver data very quickly, but at a lot of power. We try to issue 4 instructions every clock cycle, and we dynamically figure out, do they have a conflict? We speculate. We do branch prediction. We do value prediction. All of this machinery trying to make a single thread run fast. And the result is that in a modern Xeon processor, less than 2% of the power actually goes to the arithmetic units that are doing the work. 98% of the power is overhead. So there is a different way. If we compare a modern CPU to a modern GPU, we see a striking difference in how much power it takes, how much energy it takes for each flop. It takes about 7 times more energy per flop in a CPU than it does in a GPU. I'm showing here a Westmere CPU and a Fermi GPU. Both came out in 2010. Both use similar IC technology, but 7 times more power per operation in the CPU. And it's not because the CPU was poorly designed. This CPU is a wonderfully designed, very, very well-designed CPU. The problem is that they're designed for 2 separate things. A CPU is designed for single-thread performance. It has 6 or 8 cores on it. GPUs were designed not to run one thing fast. They were designed to run hundreds and hundreds of parallel tasks as efficiently as possible. They were designed for throughput of many parallel tasks. A Fermi GPU has 512 processor cores on it. Each one is very small, very power efficient. Now you might say, can we just reduce the overhead of the CPU? Can we build a more efficient CPU? And the answer is no, and the reason is CPUs have a job, and if you tried to take out the overhead of a CPU and make it more power efficient, it would become a very poor CPU. We saw this recently when AMD came out with their new Bulldozer CPU core. It was a little bit more efficient than a Xeon core. You could put more of them on a chip. And the market reaction was very negative because the single-thread performance was lower. So you can't take a CPU and turn it into a power-efficient processor without losing its performance as a CPU. But if you take a CPU and a GPU together, you can take most of the work and run it on the GPU, and then the leftover work you can run, the serial work you can run on the CPU, and you get the best of both worlds. So the world has recognized the advantages of GPU computing. Just 3 short years ago, there were virtually no independent commercial software programs that used GPU for acceleration. There was only research and experimentation going on with GPUs. Now we've seen GPUs being taken up by many different industries. The oil and gas industry uses GPUs extensively to accelerate their work and get a competitive advantage. Governments are using GPU for signal processing. The life sciences have adopted GPUs for molecular modeling, for material science. Finance has adopted GPUs for accelerating options pricing and risk analysis and Monte Carlo simulation. And the manufacturing industry has taken up GPUs. Most of the important manufacturing codes now use GPUs. And in fact, we now have dozens of independent software applications that have been accelerated with GPU computing, from virtually none just a few years ago. It's the very high end of supercomputing, though, that has most recognized the importance of GPUs and the value they provide, because they are the centers that have the biggest problems with power. 3 years ago, last month, was the very first GPU-accelerated computer on the top 500 list. Now, 3 out of the top 5 systems use GPUs. Of course, we're familiar with 2 of those systems right here in China. One of the other systems, the Jaguar system, which is the largest system in the United States, is at Oak Ridge National Laboratories. And they've just announced that they're upgrading Jaguar to a new machine called Titan using GPU computing on all of the nodes. Now, I'm particularly excited about seeing the machine at Oak Ridge because I've personally worked with the team at Oak Ridge for about 10 years now in my previous employment at Cray. And we had multiple generations of machines that were using CPU technology. And when it came time, a year or 2 ago, to look at the next generation machine after Jaguar, we all came to the conclusion that we could not meet the goals with CPUs alone. We had to use GPU computing in order to provide the performance within the power constraints of that system. The new Titan machine, when it comes out next year, will have GPUs on all of the compute nodes, over 18,000 GPUs, assuming it gets fully configured. It will be twice as fast and 3 times as energy efficient as the current #1 machine, the Cray computer in Japan. It will also be much, much smaller. And this machine will be used for tremendously important applications. Oak Ridge has a mission to produce new science in the areas of climate and energy. They're taking multiple codes and preparing them for the addition of GPUs into the Titan system next year, including codes to do modeling of combustion engines, codes to do modeling of next-generation biofuels so that we can reduce carbon emissions, so that we can reduce our dependence on petroleum. The CAM-SE code is modeling the Earth, trying to look at global climate change and understand mitigation strategies. The de novo code is modeling fusion, trying to develop safe fusion energy that could provide a non-polluting form of energy. These are applications that have huge societal benefit, and I'm extremely proud to be a part of what Oak Ridge is doing with their new Titan system. Of course, there's also been a tremendous amount of work done with GPUs around the world, including a lot of breakthrough scientific work right here in China. Jensen talked yesterday about the very first simulation of the H1N1 influenza virus done on the Mole 8.5 machine. There's a team at Peking University that has done the largest turbulent flow simulations ever performed by humanity using the Tianhe 1A system. This is important for understanding the weather, for understanding jet fuels, for understanding chemical mixing. Very important application area. And these machines are not just used by researchers locally. The Tianhe system is used by researchers all over the world, including a team at the University of California in Irvine in the United States that are doing fusion simulations as part of the International ITER project to build a fusion reactor. Now, the reason that GPUs have become adopted by so many has a lot to do with the performance, has a lot to do with the power, but it also has a lot to do with the programming. Several years ago, even 2 years ago, it was actually much more difficult to use GPUs than it is today. The pace of innovation in the software world, in the programming environment for GPUs, has really been quite astonishing. This can be demonstrated by a very brief history of GPU computing. The GPU itself is only 12 years old. It was invented by Nvidia in 1999. And by 2003, people started realizing that this device, which was designed for graphics, could be used for doing general purpose computing. And so they started using graphics APIs, such as OpenGL, to accelerate their scientific applications. So imagine trying to run a molecular dynamics code, or a weather code, or a crash code, and having to cast it into a graphics API to actually pretend that you were painting triangles on a screen and shove that code down a graphics pipeline. This was tremendously difficult for programmers, but they did it because they wanted to get at the power of GPUs. By 2006, Nvidia had realized that we should make this easier for the programmers. And Nvidia created CUDA to allow programming GPUs just like any other processor in a high-level language, in C. Now you can program in C++ or in Fortran. And it was just in 2008 that the very first GPU system appeared on the top 500 list. It started getting really interesting in 2010. This was the year that Nvidia introduced the Fermi GPU. This had good double precision floating point, which the scientists needed. It had error-correcting codes, which allowed you to build a large system and have it be reliable. This is when Cray became very, very interested in GPU computing and decided it was the right path to take forward. And now we're about to introduce the Kepler GPU next year. The goals for Kepler are to be broader, to accelerate more areas of high-performance computing, and also to be easier and easier to program. Now, we're all familiar with CUDA. CUDA has made GPU computing much more accessible to the average programmer. But there are other ways to use GPUs that are even easier. If you have problems that can be met with a library, you can call a library, such as an FFT library, a dense linear algebra library, a sparse linear algebra library, random number generators, etc. And without even knowing that you're using a GPU, the library has been enabled to be accelerated with GPUs, and it takes care of it for you. So you do nothing different than you would on a regular CPU system, and you can get GPU performance. We have a large number of libraries that's growing every year. But we're increasingly interested in a new way of programming called directives, GPU directives. GPU directives allow you to take your existing C or Fortran code and simply put in hints that tell the compiler where the parallelism is. And then the compiler takes care of generating the code to use the GPUs. It takes care of the data movement. It takes care of generating the GPU instructions. It takes care of the synchronization. And this allows the programmer to focus on just exposing parallelism and lets the compiler take care of all the underlying details. The other thing that's nice about using GPU directives is that now your code will work on multi-core CPUs as well as work on many-core GPUs. The same code will run across multiple platforms. We're so confident in this form of programming that we've decided to guarantee that users with the right kinds of codes can double their performance in just 4 weeks using directives on GPUs. We've created a program where people can download a free trial version of the PGI compiler, try out accelerators, and then report back the results. And if they can't get 2x performance, we will help them by giving them consultation to help them achieve 2x performance. And we've had tremendous response to this. Many people have downloaded the compiler, have sped up their applications, and have reported back the results. And we've seen application speedups of anywhere from 2x to 3x, all the way up to 10x, and even 20x or more. And the interesting thing is that the least sophisticated users get the best performance. People that already have very sophisticated, highly tuned codes might see a 2x or a 3x performance improvement for their applications. But the people that had poorly optimized codes, maybe they weren't even parallel, can see very, very large speedups. These are the scientists that are not computer scientists. They're the chemists and the biologists. They're the limnologists that want to study snapperfish, like Professor Black from the University of Melbourne. They're the people that want to do their physics, to do their earth science, and they don't want to think about programming. So they have a set of equations that explain their science, that explain the mathematics behind their science that they want to model. And they write some simple code, and it runs on their CPU, and it perhaps doesn't get very good performance, but that's all they want to do. They want to concentrate on their science. And those people, when they use directives, can get tremendous speedups because the compiler parallelizes their code for them, ports it to the GPU for them, and they can get tremendous performance improvements with very little effort. Very, very exciting to us. And the beautiful thing about using directives, like the new OpenACC directive standard that we just announced last month, is that the work the programmer does is making the code inherently better. The user just focuses on exposing more parallelism. They're not doing work that's platform specific. They're not doing work that is only applicable to running on a GPU. They're simply tuning their application to expose more parallelism. And when they do this work, it turns out that their application will run faster, even on a CPU system. There are two great examples here. These are two of the applications that are being tuned for the new Oak Ridge Titan machine next year. One of them, S3D, is a combustion code. The team there took the top 3 kernels that represent 90% of the runtime, and they used directives, OpenACC directives, to port to the GPU. They tuned their code so they got good performance on the GPU, and they achieved 3 to 6 times speed up on the GPU nodes compared to the all CPU nodes. But the wonderful thing about this is that the CPU version also got faster by 50%. They weren't working to port their code to a GPU. They were working to expose their code, expose more parallelism. They were working to improve their code, and the code got better across all platforms. The same thing happened on the CAM SE application. They took the top kernel, accounts for 50% of the runtime. They tuned it using directives, and they got 6.5 times speed up of the GPU compared to the CPU nodes, but the performance of the CPU nodes doubled as well because the work was spent improving the code. This is a great value to the developer. So I want to say just a few words in closing about what we're focusing on for the future. Because we're not trying to build a CPU, we're not trying to build the best single-thread performance, we can concentrate completely on power efficiency. We can make more and more efficient processors so that the Kepler processor, when it comes out next year, will be over twice as efficient in terms of sustained floating point performance per watt compared to Fermi. And we're already working hard on Maxwell, the next generation in 2014, and that will have another factor of 2 or greater than factor of 2 improvement in sustained performance per watt. There are a few things besides performance per watt that we're looking at for Maxwell. We will continue to focus on that as the most important thing. We're also focusing on broadening the applicability, trying to make GPU computing be very successful on every single HPC code, not just some HPC codes. So we're trying to make GPUs work well on smaller pieces of parallelism. We're trying to put more of the computing onto the GPU and rely less on the CPU. We're also trying to tighten the integration of the CPU and the GPU, to have them share memory, to have them be able to synchronize with lower latency, and make it more efficient to share work between the CPU and the GPU. And finally, we're focusing very much on programmability. We're going to continue to work to provide better tools and better programming models to allow more and more users who are not computer scientists, but simply scientists, to use GPUs with very little effort. So I'm pretty excited about the future of GPU computing. This is why I left Cray and came to join Nvidia. I'm convinced that GPU computing is the right technical direction. It's very hard to overstate the importance of this statement. We are constrained by power. Every generation is going to be more and more constrained by power. And you simply can't optimize for single-thread performance and power efficiency at the same time. A CPU has to be focused on single-thread performance. GPUs are focused on power efficiency. So the future of high-performance computing absolutely has to be heterogeneous. We need a few fast cores for the serial work, but most of our cores, most of our work has to be done by processors that were designed first and foremost by power efficiency. Now, does that mean that they have to be GPU computers? I believe that GPUs are the only viable path forward to our heterogeneous future, for really 2 reasons. The first is technical. GPUs are designed for power efficiency, and that is absolutely critical from a technology perspective. We have to take CPUs and GPUs together. But the other part is a business reason. GPUs have a day job. They're designed for a very, very high volume graphics market. And that large market, that high volume market, allows us to invest enough to create the world's best massively parallel processor. The HPC market itself is too small to support the development of a competitive processor, but the graphics market is very large. So by leveraging that high volume market, we can create the world's best parallel technology in combination with CPUs, and I'm convinced that that is the right path for the high-performance computing community. So with that, I'd like to thank you very much.